Okay, so last week we looked at the cross-coupled oscillator. So we finished with that, right? We started off with VCOs. We looked at the cross-coupled oscillator. So we'll continue with that today. Finish it up and then look at the other kind of oscillator, most common one, which is the Colpitts oscillator. Okay. So let's go back to this guy. So we finally arrived at this architecture here. So the nice thing, the other nice thing about this, which I guess should have touched upon last week, is remember that there's a 180-degree phase shift from each side, right? So it gives you differential outputs for free, okay? Because there's a 180-degree phase shift on each side, okay? So now let's take this again and okay, so what we're going to do is find out the input impedance of this differential pair, okay, or let's do Rn. So it's actually very straightforward. So you just put in, let's assume that there are, neglect the parasitics. So let's call this V1, we call this V2. So this is GMV2, this is GMV1, right? Okay, you put in a test source and it's very obvious, right? So it's going to end up being -2 over GM. Okay, you can try it out, it's very, very simple. Okay. Now what that means is, so now you know how to design. So if you have a certain resistance of the tank, remember we looked at the one port view last week. That is, if the tank has a certain resistance Rp, you know that the negative resistance for oscillations it should be equal, but for reliable startup you want it to be maybe a few times that, right? To loop gain is 1 is the condition, but you want a little bit higher, maybe loop gain of 2 or 3 for startup. Okay. So you will correspondingly design your GM. So obviously, if you remember, we talked about this. If the parallel resistance is smaller, that means you have higher loop gain. Remember that from last class? Kind of. Not sure. Okay. So if the parallel resistance, if you remember, we discussed the conditions for. Let's see if we can find it. Remember this guy? We looked at the condition for oscillation, right? So, remember this, right? Because they appear in parallel, the smaller the impedance is, the more effective it is, right? So, ideally what you want is, you want your active circuit, the magnitude to be less than, right? If it's minus RA, you want RA to be less than R for growing exponentials, which is the condition for startup anyways. Right? Is that clear to everyone? So obviously what that means is your GM will increase. If you need smaller Rn, right, the GM should be larger. Okay. Actually let's so let's say this is L, C, Rp. Sorry, let me do a better job of it. So let's add a current source. Okay, so obviously you've taken care of the startup oscillations, but you need to define the power in some way. So if you leave it like this, so let me complete this guy. So if you leave it like this is the oscillator we saw last class. So if you leave it like this, what happens? The gate is directly biased at VDD, okay, which means it's probably going to draw a lot of current, right? Or rather, the power consumption is going to depend on the size of the transistor, and the size of the transistor is going to depend on the inductor Rp, right? So you want to decouple these two parameters, so you would add a current source, something like this. Okay, and of course there are multiple ways of doing this. Okay, so you can add the current source at the bottom, you can add the current source here and ground this guy. Okay, there are multiple ways of doing this, and then you can have a PMOS version. Here we are just looking at the NMOS version, right? So the center tap goes to ground. Something like this. You can have a PMOS version. Okay, and again, similarly, the bias can even go here. Doesn't matter much. Okay, well, it does matter, but to the first order, it doesn't matter much. Okay. Okay, so let's just quickly analyze this guy. So let's take this cross coupled pair. Okay. So what do you know? First of all, yes. Okay, this, so what have I shown? Earlier we looked at, of course we looked at two separate inductors last time. This should obviously be a B and L. We looked at two separate inductors, right? What I did is I just made them a single inductor. Okay. I just made them a single inductor because we are going to compare it with a slightly different architecture, and you want to compare it with the same size of the inductor. That's why I did. What I called that the center tap. Okay, we call that the center tap. In other words, you need to find, so it's something like this. Okay, so this is one full inductor. What you need to find is a symmetrical point such that the inductance is equal on both sides. Like everything is equal on both sides. Okay, that's called a center tap. Okay, so you need to find something like that and use it here. Instead of, I mean, obviously that is better than using two separate inductors. Okay, in terms of area, first of all. And then what you'll find is, in terms of inductance and coupling and so on, it's also better. Okay. This capacitance is a fixed capacitance. Well, it's a combination of fixed and variable capacitance. Remember, right now we are looking at oscillators. We have not gone to the voltage control part. Okay, so right now as far as oscillators are concerned, you just need an L and a C. So this L is a design parameter, this C is not part of the inductor, it is a design parameter. You need to choose it large enough such that the inductor parasitic capacitances don't matter. Okay. Okay, so we can do that too. So remember that this thing is just a, I keep getting the wrong page. Yeah, so this thing, you can just make this a virtual ground instead of a real ground, right? So it will become C by 2, whichever way you look at it. Okay, so in this case, right, if you have a virtual ground, it will become C in series with C, it will become C by 2. So C by 2 resonates with 2L, just again 1 over root LC. Okay, I just converted that to a single L and a single C, that's all. And the C is the C which you add. The resistance is obviously not what you add, it stands for the losses in the tank, and usually the losses in the inductor dominate because remember that you have a series resistance, that times Q is your parallel resistance, right? Typically the Q of the inductor would be like we have seen, right, 8 or 9, 10 maybe maximum. The Q of the capacitor is more like 40, 30, 40. Okay, especially if you have a good passive capacitor, it can be pretty high. Okay, and that is why you almost always consider the resistance of the inductance to dominate the overall. But there are cases, I mean there are very specific cases where the resistance of the capacitance can matter, and that depends on how you choose your inductor and capacitor values. Yes. Want the rest of the? Yes. Sure. Yeah. That's right. Yeah, but it's just this thing, right? It's a, you can look at it as a virtual ground. It doesn't matter. Okay, because this is just what you're looking at. As far as your differential picture is concerned, remember it's a one port view, right? You're just interested in the overall input impedance across the differential ports. That is always going to be RP. If you have L over 2, L over 2 on both sides, you're going to have RP over 2, RP over 2 on both sides. Okay? The actual thing is this is not a physical resistor. The actual resistance is in series with the inductor. Okay, so this is just a way of representing it. That's all. Okay. So what we are going to do is, so let's assume this is IT. Okay. This is I1 and this is I2 and this is V1 and this is V2. Okay. So one of the things we are going to assume is because there is positive feedback through this loop. Okay. What we are going to assume is, and it's a differential pair with positive feedback. So we are going to assume that the current switches very fast between the two sides. Okay. So what we are going to do is we are going to assume that if you look at the current waveform, so remember, even if you take a normal differential pair, as long as the input voltage is large for the mixer, we assume the same thing. We assume that if your voltage is larger than a certain value, we assume that the current would pretty much switch instantaneously, and we assume that the current was actually a square wave. That's why we multiply it by signum of t, right? So we're going to assume the same thing here. So let's plot. What is I1 going to look like? It's going to look something like this. Okay. So in 1/2 cycle, you're going to get I1 flowing through this guy, and when will that happen? Let's say this thing look like this. Okay, V2 is going to be exactly equal and opposite, right? So during this half of the cycle, M1 is going to conduct, and during the other half cycle, M2 is going to conduct. So I2 will just be, it will be 0 for this half cycle and 1 for the other half cycle. Okay. What do we know about this? Let's write the Fourier series again. Like we have done this many times before, right? So the DC value is obviously going to be half. So you're going to have half the current on one side, half the current on the other side. Plus, we looked at this, right? You're going to have so you're going to have, all the odd harmonics, right? So what is V1? So remember, at resonance, the impedance on one side is just going to be RP over 2, right? Because L and C are going to, the impedances are going to cancel out. Okay? Okay. And so what we'll do is, what we want actually is, let's do it this way. So what is this? 2IT by pi RP by 2. Okay. So this is your amplitude on the left side. Is that clear to everyone? It's pretty straightforward, right? And of course the amplitude on the other side is also going to be the same thing except equal and opposite. So your differential output voltage, which is what you are interested in, is 2 by pi IT times RP. Okay. So one obvious thing you can see is that it does not, to a first order at least, it does not depend on the device parameters. It depends only on the bias current. Okay, to first order it does not depend on the device size. And the other thing you notice is that it is actually not, it doesn't look like it is very sensitive to the type of the device. Okay, you could have a bipolar device, as long as it switches similarly, you could have the same thing, except that you'd have to take care of biasing, because obviously the base emitter voltage of the bipolar cannot switch by more than 0.65, right? You have a problem there. So you need to take care of biasing and feedback and so on. But to a first order, output voltage can be something like this. Okay. The other kind of popular topology is a current reuse topology. Okay. Okay, so effectively what you are doing is you are reusing the current. Earlier you only had an NMOS pair, you are now adding a PMOS cross coupled pair also. Okay, so you are effectively reusing the same current, flowing the same current through the PMOS also and getting more negative resistance for the same current. So now your negative resistance is -2 over GMN plus GMP. Okay, that is one thing. So you start, yes.
Increase the sizes of that cost.
What do you mean by increasing the sizes?
Have this like comparable GM.
Okay.
If I had similar current and I can increase the, let's say for the just the NMOS, I can increase the NMOS sizes.
Yes.
I could have got the same GM rate.
You could have, but what you'll see is, next class we'll look at it. This particular, okay, first we'll see, okay, you could have increased the size of the NMOS to get the same GM. But next we'll look at what happens to the output amplitude. So that changes. That's number one. Number two, if we have time, we'll look at next class. We're going to look at phase noise. We'll see if we can touch upon this. What happens is, you'll find that as far as noise is concerned, this topology is slightly better than the NMOS only topology or the PMOS only topology. Okay, as far as phase noise is concerned. Okay, we'll look at that next class. Okay. So let's say the two voltages are like this. Okay. How does the current flow in this? So let's take the first half cycle. Okay. During the first half cycle, which NMOS is going to be on? The right side one, right? Because the gate voltage is higher, very high. Okay. Which PMOS is going to be on? Obviously the left side one. Okay. So what is going to be the current flow here? That is going to be the current flow in the first half cycle. And in the second half cycle, current is going to flow like that. Okay. So now if you plot the current through the inductor, right, what is going to look like? Right? In 1/2 cycle it's plus IT if you take a particular reference direction. The other half cycle it's going to be minus IT. Is that clear? Okay. And let us say of course that you have some RP, resistance of the tank. Okay. So obviously at resonance the inductor and capacitor impedances are going to cancel out and the current is actually going to flow through this RP, okay, which is caused by the inductor. So effectively the current is actually flowing through the inductor. Okay. So what is the fundamental? In this case the cosine. Okay. I think in fact in the other case also the way we drew it was a cosine. Yeah, this is actually a cosine, not a sine. Okay. No, this is actually a sine, sorry. The other is a sine also, right? Sorry. Okay. This is your fundamental. Right? Now, remember we worked this out for the mixer, right? The fundamental of this is actually 4 over pi. It is sine omega naught t. So, okay, so the output amplitude is 4 over pi IT RP. So what is, this is actually double. Okay, in the other case we got 2 over pi IT RP. Okay. Okay, so that's it for the cross coupled oscillator. Okay, so it's actually pretty straightforward. So you want to design for a particular amplitude and a particular power consumption. So let's say you start with the power consumption, you choose a particular current, right? Then once you know the particular current, you design for a particular RP. What do you design? You design the inductor for a particular RP. Okay, if you want to, you'll see, what you'll see is, as far as phase noise is concerned, you want to maximize your swing. So you would try to maximize your inductance, which would maximize your RP. Okay, so that would maximize the swing at the output of the VCO. So that's as far as swing is concerned. And of course the sizes, so you have chosen the current, the WRLs of the transistors you will choose based on your startup condition. Okay, depending on which architecture you choose the GM based on that. Okay. Okay. So let's look at single transistor oscillators. Okay. So these are usually used in discrete applications. Okay, so if you are building a discrete oscillator rather than an integrated circuit oscillator. Okay. The main idea is you want to choose lower number of transistors so that you have lower noise and so on. Okay, that is the main motivation. So what we'll do is we'll look at two ways of designing this. One is we'll look at the single port way, and we'll again come back to the same thing, analyze, come up with the same thing using a the feedback way of analysis. So let's take a single transistor. Let's look at the input impedance. Let's put two capacitors, one between the gate source, the other between drain source. Okay, let's look at the input impedance. So we'll put in the test source. So let's call this voltage V1, call this voltage V2. Okay, obviously this is V1. Let's do it this way. Okay. This is Gm times V1 minus V2. Okay, what is V1? So IT is flowing like this. So it's nothing but V2 minus IT times okay. So that is one relation. V1 minus V2 is minus IT over SC1. Okay, then what we'll do is, this is the gate node, drain node and source node, right? We'll do a KCL at this point, at the drain node. Okay, so IT equals n times V1 minus V2 plus times SC2. Okay, oh sorry, okay. Yes. Sorry. Oh, plus Vt times SC2. Okay. Okay, so this is what you get. Gm plus S times C1 plus C2 over S square C1 C2. Okay, so you get S square C1 C2 here and you get an extra C1 plus C2 there. Okay, so you can write this as 2, right? So if you look at the impedance as a function of omega naught, so this is your negative resistance term plus, so Okay. The other term gives you C1 C2 over C1 plus C2. That is C1 parallel C2. Okay. Yeah, I mean when I say parallel, what I mean is no, like R1 parallel R2. So okay. So let me write it explicitly. Okay. It's just a way of saying it. I mean, okay. So this is your negative resistance, and this is your capacitance, which you are going to resonate with the inductor. Okay. This is the equivalent circuit, right? Okay. So now what do you do here? So let's take this guy, put an inductor across it. Okay. C1. Okay. So if your inductor has a resistance Rp across it, okay, so you want Gm over omega squared C1 C2 less than Rp. That's number one. Okay. So now note that we didn't explicitly put any ground for any of these nodes. Okay. So you can actually get three kinds of oscillators depending on which node you ground. Okay. You can ground any one of these three nodes. Okay. Let's just go over to the next page. So if you ground the gate, you get this. Okay. So this is your Colpitt's oscillator. Okay. And if you want to show with biasing, so you connect your inductor to VDD. It looks something like this. Okay. Connect your gate to some bias voltage, add a bias current in series with the transistor. So your capacitor ladder is actually feeding back the signal from the tank. So this is your output. Okay. So you can again ground your source. So you'll get something like this. Another kind of oscillator. So this guy becomes if you add the biasing, it looks something like this. Okay. And of course the third You can ground the drain. Okay. So basically what you're doing is you're using a common collector, common base, common gate or common source. Did I say common collector? Common drain, common gate or common source amplifiers to create the oscillator. Okay, so that's what we're doing. So with biasing it looks something like this. Okay. So this is kind of the most commonly used one, the Colpitt's oscillator. Of course, I mean the exact connection of C1, C2, whether it goes to ground or VDD, that is something which changes, but the basic connection remains the same. Okay. So we'll see how we can arrive at the same thing using the feedback model. Okay. So you actually have, let's say you want a feedback. So you know you're going to create some kind of tank. Okay. So let's just draw the inductor for now. You want a feedback, and you can feedback. Let's say it goes to the drain because typically the output is taken at the drain. So now you have two options. You can either feedback to the gate or feedback to the source. Okay. Which is the correct way to do it? You know that the current and voltage have to be in phase because the resonant circuit is completely resistive at resonance. Okay. Obviously if you feedback this way, the current and voltage are not going to be in phase. So this is the right way to do the feedback. Okay. Okay, how do you do the feedback? You can do it several ways. Okay. So let's say it's like this, and you're going to do the feedback. So the first problem you have to face when you do the feedback, what is the input impedance looking in here? Approximately 1 over Gm. Okay, we'll neglect the output impedance of the transistor. So it's typically very small. Okay. Typically it's a low impedance point. So you don't want to load the tank. Okay. Remember that so if you have this, the RP over omega naught L. Okay. If you do the direct feedback, okay, and if 1 over Gm is much less than Rp, Q is very small, much smaller. So this is the loaded Q versus the unloaded Q. So you are designing an inductor for a particular Q. When you stick it in the circuit, the actual Q which it faces may be much less depending on the impedances presented to it by the rest of the circuit. Okay, that's called the loaded Q. So you want to prevent this guy. Okay, so what do? So you take this guy. So you do some kind of impedance transformation. Okay. So what easier way to do it than use a real transformer, right? So this is 1 over Gm. So let's say you have a turns ratio n is to 1. Okay. So what is seen by the tank? N square by Gm. Okay. So this is one way to do it. Okay. The other way to do it, remember that when we studied the impedance transformation during the first few classes, we looked at this guy. Remember this? The tapped capacitor. The tapped capacitor match. Let's not call this RP, let's call this something else. So let's say R0. Okay. What is Rn? Okay. This is kind of the effective turns ratio. So this is N squared of the capacitor, tap capacitor circuit. Okay. And you also have the tapped inductor. One plus L1 over L2 times, whole square times R0. Okay. So you can do either of these two feedbacks. So each one gives you a different oscillator. Okay. So you use this guy, it gives you the Colpitts. Okay. You use this guy, it gives you what is called the Hartley oscillator. Okay, so what we'll we'll just start off with the analysis of this guy. So what do we know about this guy? The yes. Definitely. What are the trade-offs? What are the trade-offs you can think of here? Direct trade-offs. Obvious things when you look at it. This is using two inductors. So of course, more area. You might be able to implement a single inductor with a tap on it. So that will definitely save on area. We won't have time to look at this in class, but there are implications for noise, depending on which circuit you use. Okay. You can. I'll put up some papers. You can take a look at it, which discuss the noise of these two circuits, and tells you which one behaves better. And also, it will also talk about the noise of the cross coupled. Okay, compared to these two guys. So the Colpitts in general is supposed to perform better with noise. Okay, as far as noise is concerned, it's supposed to perform better. The main reason is what we may not have time to get to it actually today's class. If you analyze the behavior of the Colpitts, right, the operation of the Colpitts, what you'll find is the current going through the transistor is actually in the form of pulses rather than as a nice sinusoid or a bias current. Okay, so it actually has a lot of harmonics, and it so happens that those pulses are aligned with the peak of the output waveform. Okay, in general that is much better for noise. Okay, you will see there are other kinds of oscillators where it's aligned with the zero crossing, with cross coupled, for example. Okay. So definitely there are trade-offs in choosing which oscillator you want to design. Okay, maybe let's just stop here. We'll continue next class. Okay, next class we'll continue with the analysis of the Colpitts, and we'll look at phase noise. Maybe phase noise might take a full class, so we might boil over into next class. But yeah, I think that should be it. Maybe we'll also be looking at quadrature oscillators. And maybe ways to generate. Did we look at quadrature generation? RC-CR circuits we did, right? We did look at it a few classes back. So we'll just look at quadrature oscillators and stop there. Okay. Okay. See you guys on Monday.